Hi, Assalamualaikum. My name is Muhammad Ifan Nisha bin Abdul Karim, and today I will be presenting about smart door alert system for deaf and low vision. And my project team members is Muhammad Yusuf Rasli, Amir Asfar, and Muhammad Azim bin Muhammad Faizal. And my supervisor is Muhammad Afri Elmi bin Abdullah. So, engineering social impact through Tribet Mara Ledang. We applied the social innovation to three parts: bridging theory and real-world hardware integration, designing for marginalized and undeserved communities, and pushing concepts toward commercial viability. So the innovation here is not just a theoretical, it is built to solve an immediate human friction points in the real world. So we're gonna talk about the bridging the sensory gap with the wearable haptics. So the physical environment, which is our doorbell, we send through the we press the doorbell system and then we send the wave, which is our internet, to our ESP32, and ESP32 will vibrate to the users. So the solution is a smart door alert system integrating edge computing in a custom wearable, and our dual model alerting, which is translate a physical door trigger into immediate haptic, which is a vibration, and distinct visual alerts directly on the user persons. And it always connected, remove the limitation of static well-mounted strobe light by keeping the alert on the user's wrist or clothing, no matter where they are in the home. So we're gonna take a look with our problems, which is the invisible barrier of a standard door knocks. We have the trigger, we have the gaps. So that is a difference between a traditional doorbells and my projects. So we take a look. The other trigger. Traditional doorbells rely entirely on a high frequency sound, rendering them useless for the deaf community. So the visual gaps. Existing visual alert systems are often static, localized to one room, and inadequate for low vision users who are mobiles. So the conclusion is the environment will send a signal to the and deliver it to the users, which is we using a haptic, which is vibrations.
So we move to architecture driven by edge computing and micro wearable. So when someone presses a doorbell, the Raspberry Pi will send a signal to cell SP32, and it will send a trigger that vibrate the haptic. So we will go to the instantaneous signal journey. So the first stage is input trigger. Visitor will visitor interact with the smart door module and send the signal to Raspberry Pi. Raspberry Pi uh, authenticated and process the signal locally. And we move to wireless transmission. P4 broadcast the alert protocol via local IoT network. And then we move to wearable reception. The SP32C3 microcontroller receive the signal instantly. And then we move to the final stage. Dual sensory output. Wearable triggers a high frequency vibration motor and a high luminosity LED sequence. So we move to the differences of multiple project like indoor stable. So the first project is standard doorbell. The second project is strobe light system, and the project is generic smart doorbell, and the fourth one is our system. So as you can see, standard doorbell, they fill a lot of our objective. Only the cost efficiency is passes, but for our system, we pass for all the objective. So our system offering a dedicated wearable with distinct haptics at highly efficient product cost.
Deploying where the need is greatest. First is primary target, individual households, providing independence for deaf and low vision individuals living alone or with family, ensuring they never miss a visitor or emergency knock. Second is secondary target, special education and TVET institution, Scaling the system to monitor multi-door facilities, allowing institution staff to manage accessibility across campus environment. Engineered for operational sustainability. First is power efficiency. The Seed Studio Xiao ESP32C3 is chosen for ultra low power consumption in deep sleep mode and ensuring all-day wearable battery life. Second, modular architecture. Using standard IoT components allows parts to be easily swapped or upgraded without replacing the entire system, drastically reducing electronic waste. And the third one, open protocol foundation. The software ecosystem can be continuously updated over the air and ensuring the hardware remains relevant as smart home standards evolve. Restoring independence, elevating the institution. For TVET Maraledang, this project cements the institution position as a leader in applied engineering and empathetic design. For the community, we are not just building a doorbell, we are restoring autonomy and spatial awareness to the deaf and low vision community. And the final outcome, a commercially viable, deeply impactful technology built from the ground up by Mara innovators. So for the last slide is validated, documented and ready for deployment. First, current TRL status is system has moved beyond theoretical design into active hardware integration and operational testing. Second, validation checkpoints. Latency testing complete, trigger to wearable response, haptic motor threshold testing for user awareness, network stability testing on Raspberry Pi 4 Edge node. And for the last point is supporting documentation. Full technical schematics, bill of materials, and user testing logs are finalized and available for institutional review.